Good morning, children. Today we are going to start a new chapter, that is chapter 5, refraction through a lens. Refraction through a lens. Okay. So in the previous chapter what we saw, okay, so lens is a spherical surface. Okay. Now in the previous chapter what we saw, it was a plane surface. Okay. So if it can be a triangular block or a rectangular prism. All of this are plane surfaces. Okay, so if you see the previous chapter, the heading will be refraction through plane surfaces. Now this chapter 5 is refraction through a lens. Now what is a lens? Lens is a spherical refracting medium. Okay, spherical refracting medium. Now you had convex and concave mirror last year. Same way we have convex and concave lens also. Okay. Now this lens is called convex lens, and there is another type of lens. This lens is called concave lens. Now these are called spherical because they have curved surfaces. They have curved surfaces, so they are called spherical refracting surfaces. Okay. So basically two types, convex and concave. Okay. So convex, there are basically three types of convex. This is called biconvex, this is called plano-convex, this is concavo-convex. Okay, this is biconvex, both the sides are convex. Another type is one side plane and next side is convex, that is called plano-convex. Then you have another one, concavo-convex. One side will be concave, other side will be convex. Same way, in concave also we have three types. This is double concave. Then you will have one half, okay, that's plano-concave. And then we have concavo-convex. Convexo-concave. Convexo-concave, okay. So in this is straight, this is curved. Okay, so these are the types of lenses that we are going to see. Next we are going to see the action of lens. Action of these lenses. Now convex lens is otherwise called converging lens. Convex lens is called converging lens. Okay, why is it so? The rays that are going parallel to the principal axis, they will all converge at a point. That's why it's called converging lens. Now, how is this possible? Now, to understand the action, you have to divide this into number of prisms, and so roughly I can divide this into structures like this. Okay. These are prisms and this is a glass slab. Okay, glass slab. So we take incident rays hitting on all this. Now in the previous chapter we have seen that this is a ray that is incident. Normally this will go straight. So the center ray will go straight. Now we know the function of a prism is to bend a ray towards its base. You remember the basic function of a prism is to bend a ray towards its base. So what it will do is this prism, it will bend this ray towards its base, and same way this prism will also bend this ray towards the base. Same way for this prism, base is here, so this ray will go like this and this ray will go like this. So all of them will meet at a point that is called principal focus. Okay, so parallel rays after refraction, okay, this is refraction, it's not reflection, it's not coming back, it is going into the other side and it's going to bend, but it will bend in such a way that if it's a prism it will bend towards its base. So because of that you get a convex will behave like a converging lens. Converging lens. On the other hand, concave will behave like diverging lens. Concave will behave like diverging lens. Let's try to understand it from the shape. Now because its shape is like this. Now if I divide it into number of prisms, so this will be one prism, and this is another prism, and this is another prism, and the center part will be a rectangular glass slab. So if I take rays like this, for this prism base is here, so what will happen? The ray will go upward. For this prism base is here, so the ray will go like this. This normal incidence, so the ray will go like this. This one, ray will go like this, and this one, the ray will go like this. So that is why it is called diverging lens, because the rays, parallel rays, after passing through the lens, they go diverged. But one thing, if you extend all these rays backward, if we extend all these rays backward, they appear to come from a point. They appear to come from a point, and that point is called principal focus. That point is called principal focus. Is it clear, children? Now, if you compare this with mirror, okay, concave mirror was functioning like a converging mirror, and convex mirror was a diverging mirror. Okay, so this is just the opposite. Convex lens will be converging and concave lens will be diverging. Remember that. Okay, so the first thing you have to know is the action. So convergent action of convex lens. Okay, convergent action of convex lens, and then divergent action of concave lens. These two diagrams. Now we go to the technical terms related to a lens. Like we had terms related to a mirror last year. So here we are having technical terms related to a lens. Okay. Now the first term is center of curvature. Now a convex lens can be assumed to be obtained by intersecting two spheres. Okay, if we intersect two spheres, this common portion will have the shape of a convex lens. Okay, so center of curvature definition is the center of the imaginary sphere. Now this is an imaginary sphere, it's not a real sphere, or center of the sphere of which lens is a part. This is called center of curvature. Okay, so the center of a plane, center of the sphere whose part is the lens surface is called center of curvature of that surface of lens. Then we have radius of curvature. Next is radius of curvature. As usual, the distance between optical center. Now this center part is called radius of curvature is the radius of this. So this is C1 and C2. These are the center of curvature, and R is the radius of curvature. Radius of these spheres are called radius of curvature. Definition: the radius of the sphere whose part is the lens surface is called radius of curvature. Then we have principal axis. So principal axis is line joining the two centers of curvature. The line joining the two centers of curvature is called principal axis. And then, so the definition for principal axis is, it is the line joining the centers of curvature of the two surfaces of lens. Now, another thing, convex we assume like this. For concave, we are taking, we can assume that a concave lens can be formed by this common portion will resemble the shape of a concave lens. This common portion will resemble the shape of a concave lens. So same way, the centers of these two spheres are called center of curvature. The radius of the sphere is radius of curvature. The line joining these two are called principal axis. Okay, so 3 definitions we have done so far. Then we come to the next definition, optical center. Leave off this definition, come to this definition. Optical center of a thin lens is the point on the principal axis of lens such that a ray of light directed towards it passes undeviated through it. Now, optical center is basically the geometric center of the lens, and one main feature of this point is any ray that is passing through it will go undeviated, means it will go straight. Okay, any ray that is passing through optical center will go undeviated. So that's the definition of optical center. Point on the principal axis such that a ray directed towards it passes undeviated. So you can strike off this. This is a little complicated one. Okay. Now, principal focus, we have first, second and all that. Now this part will come later. Okay, so actually you don't get any questions from A portion. A part is just like kind of introduction. Okay, now mainly you get questions from B part, which has all the ray diagrams. Okay, so principal focus, for now you remember, for convex, principal focus is the point where parallel rays parallel to the principal axis after refraction meet. This point is called principal focus of a convex lens. Okay, parallel rays after refracting will meet at a point, that's principal focus. For concave, parallel rays coming parallel to principal axis diverge, but when they are extended backward or they appear to come from a point, that is called the principal focus of concave. Okay, so this much you remember for now, and we'll straight away go to the ray diagrams. Now, I expect you to draw along with me. Okay, please pause your videos, go take your scale, pencil and eraser and come, and please draw along with me, then it will be easy for you. Okay, first we are going to see the rules. Okay, first rule, any ray parallel to the principal axis, so this is your principal axis, okay, and this is your focus. Now both the sides you will have focus. Okay, so, and 2f, you won't write C here, we write 2f. Okay, so this is focus and this is, okay, so first rule, now always you can draw a dotted line from here. Refraction, the bending will actually happen from this middle line. Okay, so any ray parallel to principal axis after refraction passes through principal focus. That is the first rule. A ray parallel to principal axis after refraction passes through the principal focus. Second rule is just the opposite of it. Any ray coming through the principal focus, now this is optical center, this is F and this is F. Now, if an incident ray is coming through focus, if a principal ray is coming through focus, after refraction, it will go parallel to the principal axis. Just the inverse of this. In this, incident ray was parallel to principal axis, refracted ray went through focus. In this, incident ray is coming through focus and the refracted ray goes parallel to principal axis. Or if you have an incident ray like this, it will go like this. Okay. Then the third one that we have done already, ray passing through optical center. Third rule is any ray passing through optical center goes undeviated. Okay, these are the rules for convex lens. Now for concave, we'll see later. Okay, 3 rules. I hope you understood the 3 rules. With these 3 rules, we'll be drawing the ray diagrams. Now, in mirror, we had 6 cases for concave and only one diagram for convex. In this, just the opposite. Convex lens will have 6 cases and concave lens will have only one ray diagram. Okay, so we'll start with image formation. Okay, image formation for a convex lens. Image formation for a convex lens. So case 1, object at infinity. Object at infinity. Now, so when you draw, I know you'll be drawing in a ruled notebook. I think I better show it in a ruled notebook for you. Okay. So what you do, when you draw the lens, 1, 2, so you can draw this 1, 2, 3, 4, 5. Okay, and draw 2 thin surfaces like this. Okay, please don't draw. Some children they usually use a D and draw like this. Please don't do this, or a compass and do this. Don't. Okay, it should be as thin as possible. Okay, so as thin as possible you have to do. So this is what it is better, instead of using a okay, I've taken 6, 5 is better. Sorry. One, 2, 3, 4, 5. Sorry, including this 5, right? So, as thin as possible. And the center point is your optical center. Now, you draw your principal axis. Okay, draw your principal axis and then take 2 centimeter. 2 centimeter, 2 centimeter. Again on the other side, 2 centimeter and 2 centimeter. This is F and this is 2F. This is F, this is 2F. So you have to have on both the sides. Okay. So first we are drawing case 1, object at infinity. Object at infinity. Okay. So generally, when we have object at infinity, we have to take parallel rays. Okay. If you remember, for any object at infinity, we have to consider the incident rays are coming parallel. So you take one ray, all your rays should be only till this. The bending should start from here. So the straight line till this, it will be straight. After that, the bending. Okay. So this is one incident ray. This is another incident ray. You can draw any 3, 4 also. Maybe you can draw one from here also. So after refraction, these rays will go passing through the principal focus. Okay. So you can draw one ray from below also, or you can just draw one ray above one ray below. That's also fine. Okay. So this is the case 1, object at infinity. In case 1 itself, you have 2 diagrams. One is object at infinity. Infinity means somewhere very, very far away. Maybe sunlight or something which is very far away. This is another case in case 1. Object at far distance. Not at infinity, not very far, but still far. Okay, not very, very far, but still it is, compared to the lens, it is far. Okay. So, in that case, the diagram will be slightly different. Okay, principal axis, optical center, 2 centimeter, 2 centimeter, same here, 2 and 2, F to F, F to F. Okay. Now, the difference between this and this is when object is at infinity, you will take parallel rays parallel to principal axis. In case of object at a far distance, there also incident rays will be parallel, but they need not be parallel to the principal axis. Okay, here incident rays are parallel. Here also incident rays are going to be parallel, but here they are parallel to principal axis. Here they need not be parallel to principal axis. So what I have to do is, I have to because I have to apply the rule, right? So one ray you take passing through passing through O, it's going to go straight. Now, from this, you just take a parallel ray and make it pass through F. Now these are the two incident rays I am taking. Are you able to see the difference, children? Here they are parallel to the principal axis. Here they are parallel to each other, but they are not parallel to the principal axis. That's the difference between at infinity and at far distance. So for this ray, how will the refracted ray go? It will go parallel to the principal axis. So they both will meet at a point here, and that's where image is formed. So this is your image A dash B dash. Okay, so A dash B dash is our image. Object we don't know, it was somewhere far away. So image A dash B dash is our image. So you get a inverted image. Okay, so characteristics we'll see later. Now come to case 2. I hope you're drawing along with me. Please pause it and keep drawing. It will be in this chapter, only these 6 ray diagrams, if you can learn to draw them properly, it's fine. You're done. This chapter is done. Okay. Now, coming to case 2. Object beyond 2F. Object beyond 2F. Okay. So, this case object beyond 2F. So you have to take your object somewhere here. Maybe you can take an object of height 1 centimeter. Okay, take an object of height 1 centimeter. Take it as AB. AB is your object. Then from end A, you're going to draw 2 rays. One ray parallel to principal axis. After refraction, how will it go? Go through principal focus. So this is your first ray. Second ray passing through optical center. So the incident ray passing through optical center, and that ray will go straight. And so your image will be formed somewhere here, and it will also be an inverted image. Okay, so here we get a inverted image again between F and 2F. You get an image between F and 2F. So here this is A dash and this is B dash. So immediately write AB object and A dash B dash is the image. Okay, and then nature of image. When we talk about nature of image, we'll do one more diagram and then we'll so case 3, object at 2f. Object at 2f. So object at 2f. So you're going to take an object here at 1 centimeter of height 1 centimeter. Okay, ray parallel to principal axis. First ray after refraction must go through principal focus. So parallel after refraction goes like this. Second ray passing through optical center and it goes like this. So they meet here and you get a image here. And you get a image here. So so this is your object AB. AB is your object and A dash B dash is your image. So you'll write AB object, A dash B dash is the image. Okay, so I think you got an idea about how to draw the ray diagrams. Next is you have to how to write the nature of ray diagram, nature of the image. So what all you will say about the size, real and inverted. So these are real image and they are inverted. Why real? Because the actual intersection, real, inverted, formed at F. Okay, focus, and then fourth one, size is diminished. It will be actually extremely highly diminished because from a distance you would have focused a big object like a bus or something and you would have got a small image. So highly diminished. In this case, when we talk about the nature, again real, inverted, where is it formed? Between F and 2F. Image is formed between F and 2F. Size, again diminished. Not highly diminished, it is just diminished. Okay, so in this case, again nature, real, inverted, and formed at 2F, size, same size. Size will be of same size. Is it clear, children? Now, case 4 and case 5, I want you to do by yourself. I am not going to draw. Object between F and 2F. Then case 5, object at F. Okay, so same procedure you follow, you will get. Okay, case 6 is slightly different. Because we'll get a virtual image here. So object between F and O. Okay, so object between F and O. So this is our principal axis and this is our F. Okay, so object between F and O. So let's take an object here. A, B, F and O. Okay, first ray parallel to principal axis and after refraction it is going to go through principal focus. Second ray passing through optical center goes undeviated straight. Now, how do these two rays look? They are going diverged. Do you think they'll meet anywhere here? No. But if I extend it backward, they meet at a point and that's where the image is going to be formed, that is here. So your A dash B dash is here. AB is the object, AB object, and A dash B dash is the image. Nature, virtual, and virtual images will be always erect. You remember, virtual, erect, magnified. Okay, it's bigger than that, magnified, and formed on the same side as the object. Okay, formed on the same side as object. So children, I hope you got these ray diagrams. So in your notebook, you are expected to draw all these 7 ray diagrams. Okay, 1, 2, 3, 4, 5, 6 and 7. Okay, and homework I will be putting in the MCB app. You can do that and send it to me. Thank you.